Alright guys, this is all about mathematical expectation. So, mathematical expectation isn't a terribly strange idea, but it is a formal idea. Now, why it's not strange is because if you take a die and you shake it over and over and over again, you'd like to say that understand that it's fair, that you'd expect to get about the same numbers of ones, twos, etc. You might draw an empirical histogram. We might get something like this. Let's say 1001, 990, 1102, 995, let's make this 1005, and we'll have a few less sixes because we all know you don't shake as many sixes, right? 900 of them. So, would you say after having done 1, 2, 3, 4, 5, almost 6,000 shakes that this looks odd, or is this what you expect? Now, theoretically, this should be just a flat, straight line, but theory is not reality. Theory is not empirical. So, is this reasonable? Well, the idea of mathematical expectation is to first come up with what you would think would be reasonable. And the first form of mathematical expectation is we begin with a function, and we're going to do a discrete function. So it's a probability mass function. It expresses a probability. And what we're going to do with this is we're going to define the expectation of a function of x in the following way. We're going to add up over all the s's in the sample space, all of the x's in the sample space, mu of x, f of x. So, what does this mean? Well, first off, let's do a very simple one. What happens if we put in a constant like 1? What's the expectation of 1? Well, the expectation of 1 is the sum of 1 times f of x over the sample space, but that's 1. But this also says the expectation of 2 is 1. Or is it? A 2 goes in there, so it's 2 times 1, or 2. So the expectation of a constant is a constant. Kind of a weird calculation. Now, let's do the following. Let's do a little bit of a harder question. Let's take a die and we're going to set it equal to 1/6 for x equals 1, 2, 3, 4, 5, 6. And we're going to do the expectation of x. Now, it's time I start talking about the capital variable x and the little variable x. So first off, the idea of a random variable is that a random variable is describing something. And so if x is going to be the random variable, we like to say that x is a value of an event. So if you have a random event in a sample space, like heads or tails, it may not have associated with it a number you want. So you define this variable, capital X, which is the random variable of S, and we give it a little number x. Now, This means we have a capital X and a little x, and they often are describing the same thing, and it's kind of confusing, but it turns out it has a huge advantage as we work with something here. Here is a PMF, and the random variable is x. Now it turns out that x takes on the numbers little x takes on the values 1, 2, 3, 4, 5, 6. And so the sample space is actually the same as the little values of x. That's not always the case, because sometimes you could have done the random variable of win might be 1 in a million, and why the random variable of lose might be the 999,999 out of a million. And the S's are the words win and lose, and they have a description. And the X's, the little X's of the random variable capital X, are now these two numbers. Okay, so what are we going to do with this random variable? Well, this is the way we write. So x in the space of x, mu of x, f of x. So this is another way that we write the expectation of x. But if it's just x there, then mu of x is 1. The function just x, I wrote that badly, let's do that again. The expectation of just x is putting x in for mu of x. Mu of x equals x. So we're doing x, f of x. So here, for this function, x is going to vary from 1 to 6, and the f of x is going to be 1/6 times x. Add up all of them from 1 to 6. And what you get is 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3. Factor out the 1/6. And you guys should recognize this as a series that's not exactly easy to add up, but a man by the name of Euler figured it up very quickly. 7, 7, 7, it's 3 sevens, it's 7, 7, 7, 3 sevens, it's 21 sixths, which goes in there what? 3 and 5, 3 and 3 sixths, which is 3.5. So there's a expectation calculated with this formula, and notice it's not a possible number x. What we frequently refer to this number is the expectation of outcomes, plural. So if you rolled the dice 3 times and you got a 2, a 4, and a 5, well, I want you to notice that 6 plus 5, which is 11, 11 thirds, which is 3 and 2 thirds. These numbers are pretty darn close to each other. So if we went back to that graph where we had almost 6,000 rolls, what we would have discovered is empirically the average of those rolls would have been very close to this number. The theoretical concept of an expectation is the average we would probably see if we shook it enough, if, in addition, this model is correct. I think some of you have seen unfair dice. Some kids will have magic dice and other things. They do certain things. Well, so whether the model is correct, yeah, that's a tough one, but the theory simply says if we have it described correctly, we should be able to see what happens over the long run. So expectation, I want you to firmly link in your mind to long-term probability. This is where we say a random event, a true random event, in a next scenario is unpredictable. but in the long run becomes predictable. This long-term probability yields predictability. The problem is, how long is long enough? Now, I can put any function I like in for an expectation. So I could ask for the expectation of 6x squared. Well, that would be the sum over the x's in that space S, or capital X, of 6x squared f of x. And if you have a formula for f of x, you can evaluate this. Now, sometimes you have formulas, sometimes you don't. But the expectation function turns out to have some very nice properties. So first off, the properties are, we saw initially, the expectation of just a constant is the constant itself. Kind of a boring property. But the expectation of a constant times mu of x, well, that's a sum of the constant mu of x, f of x, over the x's and x, which is a constant times the sum of mu of x over f of x. I'm going to suppress writing this. Constant times the expectation of x. In other words, the constant factors out of expectation. This is like differentiation and integration. It comes out. That's not like what this is. Now, it turns out that the expectation function behaves linearly, which means that if we do an expectation of a constant times mu1 of x plus another constant times mu2 of x, the expectation distributes across the addition and the constants pull out, and we get which says that the expectation function behaves very, very nicely. All right, so let's do a very specific expectation calculation with a PMF. But I'm going to make this PMF a little tricky on you. So ready? I'm going to take this function f of x. I'm going to call it cx, and I'm going to define it for x equals 0, 1, 2, 3, 4. And I'm going to say that f is a PMF. Well, it would seem that the function here doesn't have enough information, but it does. First off, you know that the sum of f of x over x equals 0 to 4 is supposed to be 1, but with the c unknown at the moment, this simply says that what you have is c times 0, c times 1, c times 2, c times 3, c times 4. That's supposed to be 1. We have 4, 7, 8, 9. 10c equals 1. Why c equals 1/5? So before you even really can do anything with this PMF, you have to make use of the fact that it is a PMF to say, oh, I know that f of x is x over 5, and x's support is 0, 1, 2, 3, 4. Now that we have a PMF, I can do some expectations. What is the expectation of the random variable x associated with this PMF? Well, by definition, it's a sum from x equals 0 to 4 of 1/5 of x. So it's 1/5 times the sum of x from 0 to 4 times, oops, my apologies, I wrote it wrong. What is the expectation of x? It is the sum over x in the support, 0 to 4, of x f of x. I dropped the original x, which is the sum from x equals 0 to 4 of x times 1/5 x, which is 1/5 the sum from x equals 0 to 4 of x squared. Now we're just going to calculate that. 0 squared, 0. 1 squared, 1, 2 squared, 4, 3 squared, 9, 5 squared, 25. So I get 10, 35, 39 fifths. And what's that? 6. Okay, let's do an example of an expectation with a PMF. So I'm going to give you a PMF, kind of a sneaky format. I'm going to say f of x is equal to cx, x is 0, 1, 2, 3, 4, without telling you c. Now, that seems totally unfair, but it's not, because you happen to know if it's a PMF, then the sum of all the values of the function is supposed to add up to 1, and plugging this in, we get c times 0 plus c times 1 plus c times 2 plus c times 3 plus c times 4. Why, we get c times 0 plus 1 plus 2 plus 3 plus 4, 7, 8, 9, 10. We get 10c equals 1. Why, we get c equal to 1/10. Right. So if c equals to 1/10, I actually know the PMF specifically. F of x equals x over 10 with x equal to 0, 1, 2, 3, up to 4. And now I can calculate the expectation of the random variable x for which this PMF is defined. Is associated with the random variable x that we talked about. And so this is by definition the sum of x times f of x, which is the sum of x times cx, but we know c is 1/10, which is c times the sum of x squared, and now it's really important that I know x starts at 0 and goes to 4, so we get 1/10, 0 squared, plus 1 squared, plus 2 squared, 3 squared plus 4 squared, and there's the x squared, and so what do we got? 10, 20, 30. Why, the expectation is 3. Now, what this says is that over a long period of time, I would expect the average of the outcomes of a random experiment, where 1/10 of the time it's 0, really shouldn't even have the 0 in there. The support doesn't exist. It's 0. 1/10 of the time it's 1. 2/10 of the time it's 2. 3/10 is 3. And 4/10 of the time is 4. Well, we would expect 3 to be the average. Now, that's how we use expectation and how we calculate it. But the algebra of expectations is pretty neat as well. I can put any function we like in here and then use the properties. For example, I could ask you for the expectation of x minus 3 times x. What would you do with that? Well, you could do this calculation and say, well, I've reduced it to the expectation of x squared minus 3 times the expectation x. Now it's common that people know an expectation of a random variable. Why? Because we refer to this as mu, the mean, or average. So that's a common number to know. As we're going to see in the subsequent section, knowing expectations of x squared, x cubed, things like that are very useful. It is very important to note that the expectation of x times x minus 1 is not the expectation of x, the expectation of x minus 1. You have to use linear properties to do these calculations, which means that if you can't reduce something to linear, then you have to do an actual summation calculation. Now, we introduced ourselves to the hypergeometric, and we introduced ourselves to the uniform distribution. So, we should know what the expectation of these. I refer to your book for the expectation of the hypergeometric, but in the case of x being hypergeometric, the expectation of x is n times n1 over n. And believe it or not, that makes sense when you look at the hypergeometric in small enough cases. You can see that, oh, I'm looking for characteristic n1. That's what x is counting. That's the proportion of them, n times it. It's a little bit harder to see on a much larger scale, but it's pretty nice. I think you all should go home and do the expectation of x when x is uniform. Pick some interval from S1, S2 up to SK and have them increment by 1 and then calculate this. Because on the inside and the covers of your book, they do list these expectations. This is a good one, hint that you should learn how to count. All right, that's it.